Hello, Steinhauer here. Welcome back. We left off with Johann Kepler and his realization that if he abandoned the strict requirement that planets orbit in perfect circles or perfect spheres, that he could perfectly match Tycho Brahe's observations. And this is led him to discover three laws, actually, of planetary motion. He'd be a famous guy if he discovered one law of planetary motion, but he, in fact, discovers three full laws of planetary motion. So before we get to those laws in particular, let's define what an ellipse is. Maybe you've heard of an ellipse, maybe you know what it is, maybe you don't know what it is. An ellipse is an oval, but it's not just any ovular shape. It has a particular pattern and particular shape. This is a graph that kind of helps to show how that works. So for instance, how do you draw a perfect circle? Well, one way to draw a perfect circle is to hammer a nail in a piece of paper and take a string, attach it to a pencil, and move the pencil around that nail. All points on this ellipse have exactly the same distance from this nail, and that's what makes it a circle. You have the center of the ellipse, center of the circle, and all of the points around it are equidistant from it. And this method of tying a string around a nail is one way to draw a circle, a perfect circle. An ellipse is very similar to a circle, except that instead of one nail, you've got two nails. And instead of a single piece of string, you've got a string that's wrapped between both of those nails and a pencil. If we were doing this lab in person this semester, you'd actually in lab do this exercise of drawing your own ellipse. But what is this set? So basically, the ellipse is drawn the same way. You stretch the string out and you draw the ellipse or the set of points that would be drawn out by this particular method. This ensures that the sum of the distances between this point, which is one of the focus points, and any point on the ellipse and the other focus points, the sum of those two lines is always the same for any point on the ellipse. Because this distance never changes, it must be the case that if it's a single string that isn't being stretched, this distance plus this distance is always the same. And so it's kind of like a fancy circle, except instead of one special preferred point, you've got two special preferred points. And this is the set of points that has the same distance between it and combined between both of those two focus points. We can and will, and it's going to be important to define different aspects of this ellipse. It's going to be important later. So one is the two, just like the center of a circle is an important point of a circle, these two focus points are the special points on the ellipse. And if you're interested, I'll be saying this word a lot. The plural of focus is foci. So if I say foci, that's what I mean. I mean more than one focus. So just be aware of that. Great. So we can also define other aspects of this ellipse, just like we can define the radius and the diameter of a circle. Well, the circle doesn't have any preferred direction. An ellipse does have a preferred orientation, right? There is the long axis and there is the short axis. And we call the long axis the major axis. That goes through the two focus points. It's the longest line you can draw between 2 points on the ellipse. And we call the short axis the minor axis. And this is the shortest line you can draw between any 2 points on the ellipse. So there isn't a single diameter. There is a major axis and there is a minor axis. And you can also define, sometimes it's useful, and we will actually make a lot of use of this, to define half of those axes. So the semi-major axis, semi just meaning half, is half of the major axis. And the semi-minor axis is half of the minor axis. So we're actually going to be using this one a lot this semester, the semi-major axis. I'm going to say semi-major axis a lot. What do I mean? I mean, if you've got an ellipse, it is half the distance of the total across the long axis of the ellipse itself. Great. You can also define, depending on how long your string is and how close together your two nails are, you can make different shapes of ellipses. You can have, and we call the different shapes the different eccentricities or ellipticities. And so, in fact, a circle is a form of an ellipse, just like a square is a form of a rectangle, that happens to be the eccentricity 0, where the two focus points, the closer the two focus points come together, the smaller the eccentricity is. If they come both to the center, then you've got yourself a circle again. So a circle is an ellipse with eccentricity 0. The farther away you get those two focus points, the more eccentric or the more elongated that ellipse becomes. So that brings us to our next thing. I apologize that some of my numbers and letters got messed up here, but that's okay. We'll draw them in anyway. So the eccentricity of an ellipse. This is an important thing. I'll be talking about this a little bit. The more elongated your ellipse is, the more highly eccentric it is. And we can quantify it. We can define the eccentricity of an ellipse. We'll define how to do that, calculate the eccentricity in a bit. But for now, let's just show you, get some intuition on what these eccentricities look like. So here is a perfect circle. This is E equals 0, a perfect circle. This doesn't look much more elongated than this, but this is actually already a fairly highly eccentric ellipse. On the scale, this is E equals 0.5. By the way, the eccentricity is always a number between 0 and 1. It cannot be negative, and it cannot be 1, even 1 or greater. In fact, it cannot be 1 and still be an ellipse. So it's between 0 and 0.9999 as far as you want to go. But once you get to 1, you're no longer an ellipse. So that's 0.5. This is up E equals 0.7. This is E equals 0.9. The closer you get to 1, the more elongated it gets. 0.95. And this is 0.99. So again, you don't have to, the point is not to be able to look at an ellipse and recognize exactly what eccentricity is, but you should know that eccentricity has to be a number between 0 and 1, and that the more the greater the number is, the more highly elongated that ellipse becomes. Okay, great. So on to Kepler's laws. What are Kepler's laws? Kepler's first law says that, and this is the major breakthrough that he made, the orbit of each planet around the sun is an ellipse and not a circle. And not only that, the sun is not at the center of that ellipse, it's at one of the two focus points of the ellipse, one of the two foci of the ellipse. This was his major breakthrough. And once he did this, with his other two laws, he was able to completely accurately predict exactly where Mars and all of the other planets would be. So let's just take a look at this. Again, the planets orbit in ellipses, and the sun is at one of the focus points of the ellipse. So interestingly, there's another focus point over here, and that's just a point in empty space. There's nothing special or physical or anything special going on at this focus point. It just happens to be there. Again, you can define the semi-major axis of this ellipse, and I'll define these two in more detail later, but let's actually see these. There are special points on the orbit of every planet. This point, which is the closest the planet ever gets to the sun, we call that perihelion. Helion being the root word that means sun, and peri meaning closest to. And then aphelion is the furthest, is a point in its orbit when the planet is furthest away from the sun. Again, ap meaning furthest, and helion meaning sun, furthest from the sun. You might have heard of these terms in terms of the Earth as well. If you have satellites orbiting the Earth, they also orbit the Earth in ellipses, and you can talk about the closest point to the Earth and farthest point from the Earth, and we call those 2 points apogee and perigee, geo being the root word that means Earth, so closest to and furthest from the Earth. It works very much the same. Okay, that's Kepler's first law. Planets orbit in the ellipses, and the sun is at one focus point. Great. Kepler's second law. If he'd only come up with that first law, he'd still be famous, but he did not. He went forward and discovered two more fundamental laws of planetary motion. So Kepler's second law is this, and it's easy to say, but it's harder to understand, and the implications are quite important. So let's take a look at this. As a planet moves around its orbit, it sweeps out equal areas in equal times. What does that mean? If you stretched a string between the sun and a planet, you could imagine that string sweeping out an area as it moves around the sun, right? So for instance, this area A is swept out in the time that it takes this planet to go from point 3 to point 4. And this area B is the area that is swept out in the time it takes this planet to go from point 1 to point 2. If point area A and area B have exactly the same area, are the same, then it must be that the time that it took to go from 1 to 2 is exactly the same as the time it took to go from 3 to 4. Okay, that's the law. Equal area and equal time. It's easy to say, but what does it mean and what are the implications and why is it important? Well, it implies that planets cannot be in constant velocity as they move around the sun. They have to be changing in velocity, right? When a planet is closer to the sun, this imaginary string that's drawn between the sun and the planet is shorter than that imaginary string when it's on this side of the sun. And so in a certain amount of distance in this direction, it's going to be sweeping out way more area over here than it is over here, which implies that the sun, the planets must be moving much slower when they are on the far side of the sun, when they are furthest away from the sun, when they're at aphelion, and they must be moving fastest in their orbit when they are at perihelion, when they are closest to the sun, because this string is much shorter here, and it's going to take a lot, in the same amount of time, it's going to have to have moved a lot further in order to have swept out the same area here as it swept out when it was on the other side of the sun. So this implies that planets orbit faster when they're close to the sun and slower when they're further away from the sun. And not only that, the speed of a planet, at the velocity, the speed at which a planet is moving around the sun continually changes as it moves, because as it moves from very close to the sun to further away, that string is getting longer and longer, and so it must slow down as it moves out to the outer part of the orbit. And then when it reaches this point, it's reached its slowest point, and it starts speeding up again as it moves back. We'll see some demos of how this actually works. You'll see, even in lab last week, you saw examples of how this works in the solar system as you watch the planets, and especially the comets, move around in their orbits. Things move fastest when they're close to the sun and slowest when they're furthest away from the sun. Okay, that's Kepler's second law. Let's move to Kepler's third law. Kepler's third law, oh, it's messing up my formatting. I'm gonna have to figure this out as we go along. I'll check this. Let me rewrite this. Kepler's third law is p squared equals a cubed. Those should be superscripts. P squared equals a cubed. Okay, let's just define these real quickly. P is the orbital period of a planet. In other words, how long does it take for that planet to travel all the way around the sun once and come back to the same point in the orbit? And this is important. For this particular equation, the units matter. This equation only works if you put in the right units. And in this case, the period must be in years. And what is A? A is the semi-major axis of that planet's orbit. And the semi-major axis is, we've already defined it, half of the distance across the major axis of that ellipse, of the ellipse of that planet, right? It is how far it is through both of the focus points, which includes one of the sun, from the perihelion point to the aphelion point. Let's just go back and look at what that semi-major axis looks like. This is the semi-major axis here, right? Why is this an important unit? In fact, semi-major axis is really the only one of these ellipse dimensions that we're going to be using in any detail. And it's important because this is kind of like, if you think about it, the average distance between the planet and the sun as it goes around, right? Sometimes the planet is closer than the semi-major axis. That distance is smaller. Sometimes the planet is further away than the semi-major axis. But on average, if you do some average, it is true that the average, something like the average distance between this planet and the sun is about the semi-major axis. And so you'll sometimes hear me say the average distance between a planet and the sun. I'm really mean the semi-major axis of that planet's orbit. You can kind of think of those two interchangeably. Semi-major axis of orbit, average distance between that planet and the sun. Okay, let's go back. So the semi-major axis also has preferred units. And the preferred units for the semi-major axis is kind of weird. Let's write them down in astronomical units. Or if you prefer and don't like to write that out or say that very much, which I don't, AU. And what is the definition of an astronomical unit? You might say it's probably the worst named unit in all of science, the astronomic unit. If you didn't know what an astronomical unit and someone said astronomical units, that could literally be anything in astronomy. Of course, it has a specific meaning, and an AU, one astronomical unit, is defined to be, that gets a triple equal sign, the semi-major axis of Earth's orbit about the sun. So this is important. The orbital period in years squared is equal to the semi-major axis of the planet's orbit in astronomical units cubed. There are two kinds of equations we're going to be using in this class, one of which demands that you put in the right units. You plug in years in this particular case, and you get out astronomical units. If you plug in astronomical units, you'll get out years. If you use any other units, you will get it wrong. This only works if you use years here and astronomical units here. The other kind of equations that we use this semester all have some sort of constant here that will set the units for you. That constant will have units, and that will determine what you have to use for A or P in order to make it work. This equation really does have a constant here. That constant is just 1, and it happens to be something like years squared per astronomical units cubed. But we don't have to worry about that, because if we know, we plug in orbital period in years, we get out semi-major axis in astronomical units. Okay, real quickly, does it work for the Earth? That's always a good idea to do a sanity check. Well, what is the orbital period of the Earth in years? I'll let you think about it. It's 1. In fact, that is the definition of a year. The definition of a year is the orbital period of the Earth. The definition of an astronomical unit is the semi-major axis of the Earth. So by definition, P for the Earth is 1, and A for the Earth is 1. 1 squared is 1. 1 cubed is 1, and 1 equals 1. So this formula does work for the Earth, and the interesting thing is that it works for every other planet in the solar system. And not only does it work for every planet in the solar system, it works for every other object that's orbiting the sun in the solar system. Okay, I'll stop there, and our next video will be some examples and some math where I show you how these equations work, and we apply them to specific instances in astronomy. So stay tuned.